In this problem, we want to solve by using the Gauss-Jordan elimination. In order to use the Gauss-Jordan elimination, we want to make sure that the system of equation is written in the proper format. In the sense that we want to make sure that all the x's are lined up on the left, all the y's lined up on the left, and all constants lined up on the right before we write it in an augmented matrix. Since the problem is written in the proper form, let's go ahead and write the augmented matrix as a 2 by 3 matrix. And the first row being 5, 3, and -1. Second row being 1, 1, and 1. Once we have the augmented matrix, we want to get the first column, first row, to be a 1. One way of doing that is to multiply the row 1 by the reciprocal of 5. But as you can see, the number below it is actually a value of 1. So by using the first operation, we can actually going to take row 1 and switch it with row 2. Once we get the first row, first column to have the value of 1, we want everything underneath it to have a value of 0. And in order to do that, we're going to use the rule where I'm going to multiply to the 1, add it to the 5, so it has a 0 value. So what can I multiply to 1 that when I add it to 5 will make it 0? That's going to be the opposite. So what we're going to do is we're going to take -5, multiply it to the 1, add it to row 2, and the answer is in row 2 because that's where I want the 0 to be. So -5 times row 1 is -5, -5, -5. Row 2 is 5, 3, and -1. And my new row 2 is going to be 0, -2, and -6. Row 1 does not change. Once we get the first column to have the 1 in the first row and everything else underneath it be zeros, let's move to column 2, and we want row 2 to have a 1 in its spot. The easiest way to get a 1 is to multiply that row by the reciprocal of -2, and the reciprocal of -2 is -1/2. And we're only going to apply it to that row. So we're going to take -1/2 to each number in row 2. So that's -1/2 times 0 is 0. -1/2 times -2 is 1. -1/2 times -6 is +3. The last thing we need to do is in the second column, we need to get that all the zeros above the 1. And the way that we can do that is to multiply the second row by -1. We're going to add it to row 1. And since we want the 0 to be in row 1, that's where we're going to put the new row. So -1 times row 2 is 0, -1, -3. Row 1 is still 1, 1, and 1. And your new row 1 is going to be 1, 0, and -2. So your final matrix is going to be 1, 0, -2, 0, 1, +3. Remember, the first column represents the x, the second column represents the y, and the last column represents the constant. If I write this back in the equation form, that gives you 1x plus 0y is equal to -2. 0x plus 1y is equal to +3. And with that said, that means that x is going to equal to -2 and y is going to equal to +3. The first number in the constant represents the x. The second number in the constant represents the y. Now in this next problem, we still want to solve by using the Gauss-Jordan elimination. Now remember, in order to use the Gauss-Jordan elimination, we want to make sure that the system equation is written in the proper format, where all the x's and y's are on the left-hand side, and all constants are on the right. So for me to do that to this problem of 2x is equal to 5 minus 3y, and 4x is equal to 11 minus 7y, we want to add 3y to both sides on top. And we want to add 7y to both sides on bottom. Once we have it in the proper format, the augmented matrix would be 2, 3, 5, and 4, 7, 11. Remember, x represents the first column, y represents the second, and the vertical line represents the equals, and the last column is your constant. So starting with your augmented matrix, first thing you want to do is work in the first column and in the first row. We want to get the 2 to be a value of 1. If there is a 1 anywhere underneath that first row, then we could switch it. But since we don't, the easiest way to make a number into a 1 is to multiply by its reciprocal. And we're going to multiply by 1/2 to row 1. And we're going to leave it in row 1. And that's going to give me 1, 3/2, 5/2. And row 2 stays the same. Once you get the 1 in the first row, everything underneath it needs to be 0. And we're always going to multiply to that row 1 if we're in column 1. So the question we need to ask is, what can we multiply to 1? That when we add it to 4, we'll make it 0. And that would be the opposite. So we're going to multiply by -4 to row 1. We're going to add it to row 2. And since I want the 0 in row 2, that's where my new row is going to be. Multiplying -4 to row 1, I'll take -4 times 1, which is -4. -4 times 3/2, which is -6. And -4 times 5/2, which is -10. I want to add that to row 2, 4, 7, 11. And my new row 2 is going to give me 0, 1, and 1. Row 1 stays the same. My new row 2 is 0, 1, and 1. And we are now done with the first column. Since we're done with the first column, let's move to the second column. That means we need to make sure we get the second row, that position right there, to be a 1. It is a 1, so we don't have to do any extra step. Next, let's get everything above it to be a 0. So what can I multiply to the row 2 value 1, that when I add it to row 1 value of 3/2, will make it 0. And that's going to be the opposite of that 3/2, which is -3/2 times row 2, because that's where the 1 is. Add it to row 1, because that's where we want the 0. And we're going to put it in row 1, because that's where I want the 0. So -3/2 times row 2 will give me 0, -3/2, -3/2. Add it to row 1 of 1, 3/2, and 5/2. And my new row 1 is 1, 0, and 2/2, which is 1. So row 1 is 1, 0, and 1. Row 2 is 0, 1, and 1. Since I have my identity matrix left of the vertical line, that means that I am done. Writing it as a system, I give me 1x plus 0y is equal to 1. 0x plus 1y is equal to 1. And therefore, x is equal to 1 and y is equal to 1. Let's see what happens with this problem. Again, we want to solve it by using the Gauss elimination. It is in the proper format that it needs. So the matrix itself is going to be my x column, y column constant, -2, 6, and 4, 3, -9, and -6. I want to get the first column, first row, to be a 1. Again, the easiest way to do that is to divide by that number or multiply by its reciprocal to that row, and it only affects that row. So I want to take each number and I want to divide by -2 or multiply by -1/2. Gives me 1, -3, and -2. Next, I want to get the rest of column 1 to be zeros. So what can I multiply to the 1 in row 1 that when I add it to row 2 will make it 0? And that's going to be the opposite of 3, which is -3. So -3 times row 1 is -3, 9, and 6. And when I add it to row 2, I get 3, -9, and -6. So I get all zeros. When you get all zeros, then you need to stop and evaluate what you have. So in terms of the augmented matrix, I have 1x minus 3y is equal to -2. 0x plus 0y is equal to 0. Does 0 equal to 0? True. Anytime you have a matrix where the bottom row is all zeros, that means you have what's called an infinite many solutions. That means it is a dependent system. It is consistent. But in terms of the answer, what we need to do is take the top equation and solve for y. And that's why it's as an ordered pair, it's going to be x, comma, 1/3 x plus 2/3. That's how you do a dependent system. So in order to get the ordered pair, the second variable is going to depend upon the first one. Again, that happened when you have an augmented matrix where the bottom row is all zeros. So we should look at a problem where it's infinite many solutions. Let's take a look at a problem that would be a no solution. Again, this system is in the proper format. So the augmented matrix is going to be 1, -3, 8, -2, 6, and 3. First row, first column is a 1 already. Next, what can I multiply to that 1? That when I add it to -2 will make it 0, and that would be +2. When you do 2 times row 1 plus row 2, you get 0, 0, and 19. And the way that we interpret this is we have 1x minus 3y is equal to 8. 0x plus 0y is equal to 19. Does 0 equal to 19? That's false. That means it has no solution. That means it is an inconsistent system, but it is still independent. So if you get a bottom row where all but the last number is 0, then that is a no solution. If the whole row is 0, it is dependent. If all but the last column is 0, that means it is no solution.